Perfect. Hey everyone, thanks for joining the session today. My name is Harini Rajendran. I'm a senior software engineer with a company called Confluent, which is based out of the Bay Area, but I actually live in Chicago. I've been in the tech industry for about nine plus years now as a backend software engineer. I started volunteering with Women Who Code during pandemic, and I'm one of the leads for the Women Who Code San Francisco chapter. So today's session is going to be like a basic introduction of Apache Spark. If you're someone who is interested in data engineering, big data technologies and stuff, and if you're interested in knowing more about Apache Spark, then this is the session for you. Before diving into the session, I'd just like to mention that I'm by no means an expert in the topic today. I know some basics that I would love to share with you also. If you have any questions, feel free to ask. If I know the answer, I can answer right away. If I don't, I'll do some research and get back to you on our Slack channel. During the session, Ashwini will be sharing some useful links, and our Women Who Code Slack space invitation and the link to our Slack channel, etc., would also be there. So if you're not a part of the Slack channel and the Slack space already, please take a look at those messages shared by Ashwini, and you can join using the invitation link that's present there. Yeah, having said all of that, we can jump into the session. So before jumping into Spark, I wanted to give a little bit of a context around it, and then start talking about Spark. So first I'll be talking about why we need distributed computing. Why can't we just do all computing in just one machine? And then how it evolved. It all started with Hadoop MapReduce. Why is Hadoop MapReduce not enough? Why did we move to Spark? And then we talk more about Spark. Why Spark? What is its architecture? What are some of the common use cases for which Spark is used? What are the abstractions and the APIs that Spark exposes? And then finally, I'll be talking about batch processing pipeline using Spark. That's one of the projects that I worked on in my previous workplace. And then finally, I have like a very simple demo, a Python Spark code that I'll be running. And finally, I'll save some time for the Q&A. So yeah, so why do we need distributed computing, right? So let's take these two problems as an example. Let's say there's this array of numbers. There are like 10 numbers there, and you want to find the maximum from the 10 numbers, right? Since it's just 10 numbers, it's pretty straightforward. You can probably apply any sorting algorithm in memory and then just return the maximum number, or you can just go number by number and keep track of maximum at any point, and then you go till the end, find the maximum of the whole array and return it. It's just 10 numbers. You can easily manage the memory and everything, and you can do it pretty fast in the order of few milliseconds. Similarly, let's say you have a file which has like probably 100 words in them, and you need to count the number of occurrences of each word. Again, it's just 100 words and it's a small file. You can just read the whole content of the file in memory and just go over them one by one, count the occurrences and just return it to the user, right? So these are very simple problems which you can definitely solve in one machine. You don't really need distributed computing there. But if we just you consider the same problem, but then just increase the scale of it. For example, find the maximum number from a file. Let's say that it has trillions of numbers in them. And then similarly, like count the number of occurrences of each word in a file, which is, or in a lot of files, which is worth multiple terabytes of data. So the problem is the same, but then the scale of data that is being supplied to that problem is not huge, and no one system can handle such a scale of data. So that's where distributed computing comes into picture. So now what we can do is we can divide that huge file into smaller chunks, spread it across, like hundreds of machines. Each one of them would work on a subset of the data. They would do some processing, and then finally we would get the actual result of interest. So as the data grew, the scale of data grew, and when we weren't able to fit the data in one machine anymore, at that point, we started thinking about distributed computing, and the first distributed computing platform, essentially, like this is what I was talking about. The first distributed computing platform that became famous and that was used ubiquitously was the Hadoop MapReduce framework few years back. So what's a Hadoop MapReduce framework? It's something like, it's a distributed computing framework where there are like two different phases. The first phase is called the map phase, and the second phase is called the reduce phase. So essentially, the huge input that we were just talking about is split into like multiple chunks, and each chunk would be handed over to one of the mapper program. So they would be doing some work on the data. It would generate some intermediate result. I'll explain with an example on the next slide. But at a high level, mapper does some work, generate some intermediate result, and it would store that intermediate result on disk. And then the reducers would then read all of those intermediate results from disk. Does the reduce job, like it does some more work, and then the final output result is stored in disk again. So this is how the Hadoop MapReduce framework works in general. So here each mapper runs in its own process. It could be a separate node in itself, and similarly each reduce job would be running in its own node. So essentially that's how data is distributed, and that's where the distributed system, the distributed computing concepts come into picture. So to give a concrete example for the Hadoop MapReduce framework, let's take the same word count example, right? So let's say we have like a file which is multiple terabytes or petabyte in size, and we want to count the number of times each word occurs in that huge file. So here, for example, let's say we have split that file into 3 chunks, and we give each chunk to one map program. So what the map program does is it only counts the word and its count that is passed to it. So the first mapper says, hey, I have how ones, many ones, cookies ones, and could ones, and all the mappers does the same thing. It just counts the words for the chunk of data that it got. And then these are the intermediate results. So these intermediate results are stored in disk. And then the reduce job, actually what it does is now data gets sharded. So let's say cook, the word cook is present in the second mapper and in the third mapper, right? And then the word cookies is present in the first mapper and the last mapper. So a subset of the keys would go to different reduce jobs. Like here, for example, the top reduce job is responsible for these particular 3 keys. And the second reduce job is responsible for these particular like 4 or 5 keys. Let's say like there is some hash algorithm which determines which reducer is responsible for which key. And then all the keys that are allocated to that particular reducer would be read by that reducer. So now what the reducer has to do is, now it has all the keys, a subset of the keys along with its count. So now the intermediate result, which is read by the reducer just processes that and then outputs the final result again back to the file system. So now at the end of it, we got the result that we want, which is each word and its occurrence. So here we have taken like a simple example, but you can extend it to like multiple petabyte file with thousands of mappers and hundreds of reducers doing the same thing essentially. And then at the end we get the word count that we want. So this is at a high level how the Hadoop MapReduce framework works. It's, as I mentioned, the mapper reads data from file system. It produces some intermediate results, which is again stored in the file system on the disk. The reducer reads from the disk again and then writes the output to disk again. So Hadoop MapReduce is basically a disk-based system. It runs on something called as a Hadoop distributed file system. It's again a distributed file system. So to an end user, it would appear as if the whole file system is sitting in one machine, but at the back end, it's actually like a distributed file system where data is spread across multiple nodes. These are the things that we already spoke about. There are two phases. The input data set is divided into smaller chunks and it's handed off to the map task. The intermediate results are stored in disk and then the reduce tasks would read them. This is also an offline system. So what I mean by an offline system is when the program starts, when the mapper starts, we need all the data to be available so that we can divide them into chunks and give a chunk to each mapper. So the entirety of the data set should be loaded at the beginning of the map phase. So we need all the data. So that's why it's called an offline system. What are some of the pros of using such a disk-based system? One thing is the failure recovery is pretty straightforward here, because even if a map crashes or let's say anything happens, a reducer crashes or anything, all the data is stored, the input data as well as the intermediate data is stored in the disk. So we can always reread them and reprocess them. So it's easy to recover when anything fails. But then the cons are high IO cost, because we are reading from disk and writing to disk every time. And then like data is again reloaded at every stage from the disk. So it's not as fast because disk IO usually is quite intensive. So that's one of the downside of using a disk-based system. So that's where they thought, okay, disk-based systems are fine, but then we could do better. That's when the memory-based distributed computing systems came into picture. And they are much better because now there is no heavy IO cost to store intermediate results. The system actually persists the intermediate results in memory. And since the data is stored in memory, like we read the data from the disk, the input data from the disk, we run some logic and the intermediate result is stored in memory, and then we run some other logic by just reading data from the memory and then again storing that intermediate result in memory again. So you can keep doing such iterative workloads. You can read something, do some transformations, store it in memory again, read that, do some more transformations and store it in memory again. But the downside is it's sensitive to the availability of memory. So such memory-based systems usually need like nodes with like huge memory, like 400, 500 gigs of memory even, because all the intermediate results are stored in memory. And then let's say a node failure happens, and if something gets restarted and stuff, there is a possibility of data loss because the intermediate results are again stored in memory. So we'll have to do all the processing from the beginning once again. So that is again some of the downside of using such a memory-based system. And Spark is an example of such a memory-based distributed computing framework. So that's why it became famous, because the disk-based systems were slow. So it's like a general purpose distributed data processing engine, and it does most of the computing and stores all the intermediate results in memory itself. And usually it doesn't store anything on the disk until and unless memory is completely exhausted. At that point is when it would spill some data to the disk. Otherwise, everything runs in memory and it is super fast. So why do we need Spark? Because it addresses a lot of shortcomings from the Hadoop MapReduce framework. because it processes and stores data in memory, in cache and not in disk, it's actually like a 10 to 100x faster than Hadoop MapReduce. Again, as I mentioned, the Hadoop MapReduce framework is an offline system. You need all of the data upfront, whereas Apache Spark, it's more of a real-time framework. So you can load the data as and when it is generated, and you don't need all the data upfront. You can use Spark for batch processing use cases. You can use it for real-time use cases. You can use it for, since it's very good at doing iterative operations on huge volume of data, it is greatly suitable for machine learning operations too. So you can do like multiple different things using Spark. And Spark supports multiple like famous programming languages. Like you can write code in Java to run on Spark, you can write code in Python, or you can use Scala too. And as you all know, Java and Python are pretty famous, and it's one of the top 5 or 6 programming languages, right? So since Spark supports this, that's also one reason why Spark is very famous. Let's say someone has been using some Hadoop distributed file system, and they had their Hadoop MapReduce framework set up on top of that. If they want to switch to Spark, Spark has the ability to run on top of the existing Hadoop distributed file system as well. So that's one advantage. It's easy to migrate from MapReduce framework to Spark, and they don't even have to think about switching to a different file system or anything. And then another thing is, like in the MapReduce job, I showed you all the map tasks and the reduce tasks, right? So there, each map task and each reduce task is its own process, which means each map task and reduce task has its own JVM, which is the Java virtual machine. And running one JVM for each task is quite heavyweight. And usually the JVM boot up time and everything is pretty high. So that's one reason why Hadoop MapReduce framework is not as fast. Whereas if we take Spark, the tasks in Spark are just threads within one JVM process. We'll be talking more about it in the architecture slide. So the Spark tasks are a lot lightweight compared to Hadoop MapReduce tasks, and hence it's a lot faster than Hadoop MapReduce framework. So that's again one reason why people prefer Spark. Because these are threads and they all share the resources, and there is no like JVM involved for each task. The task startup time is usually faster. The startup time is a lot less, and so it's faster. There is better parallelization, and then since all the threads are sharing resources, there is better CPU utilization, etc. So these are some of the reasons why Spark became so famous and took over, Hadoop MapReduce framework. Yeah. So now let's spend some time talking through the Spark architecture. So Spark actually follows a master-slave architecture, or you can call them a master-worker architecture. So these are the worker nodes or the slave nodes, and there is one master node. The master node hosts something called as the driver program, and the worker nodes actually hosts the executor programs. As you see, the executor is a process, and all the tasks that are running within the executor are just threads. So there is only one JVM within each worker node. And the tasks actually run in these worker nodes. And as I mentioned earlier, they store all the intermediate results in memory. So they use cache for it. And the driver actually has the Spark context object. So the Spark context object is the object where, we have information about the Spark cluster and everything. So that is also when you write code, the driver program is where the main, the entry point of the code will be executed. So the driver program is actually responsible for orchestrating the whole task, the tasks for a particular Spark job that you're running. So let's say you're submitting a Spark job to the driver program. The driver program would say, okay, hey, I need 5 tasks. And then what it would do is it would work with the cluster manager and say, hey, I need 5 tasks. And the cluster manager will take care of finding out, okay, which nodes are free, where should those 5 tasks go, and all of that. So the cluster manager's job is to do the resource administration, the resource allocation, but then deciding how many tasks to run, where, and collecting all those intermediate results and combining them and giving it to the end user, and all of that is done by the driver program. And the Spark logic that you write, where you are actually doing the data crunching, those tasks would get executed on the worker node. Only the entry point is on the driver node, but the actual data crunching happens within these tasks in the worker node. So this is the overall architecture. The driver program has the context. The cluster manager takes care of allocating the tasks to nodes, and then the actual nodes have executors which actually runs the tasks, stores the intermediate results in cache, and then finally, when all the processing is done, a subset of the final intermediate result to be sent back to the driver program. It would merge the results and then give it back to the person who initiated the jobs. Again, here it's the same thing. The cluster manager is responsible for allocating resources. We spoke about all of these already. So this is the high-level architecture. There's one master node and multiple worker nodes, and the cluster manager is there for all the orchestration and resource allocation. And coming to the use cases, what are some of the use cases where Spark is generally used? As I mentioned, Spark is used for real-time data processing. So data could be like real-time data streams could be generated by various systems, like, when you're running some programs and a lot of microservices, all those systems usually spew a lot of logs. So if you want to do some kind of analysis on the logs, then Spark is a great use case there, because you can continuously feed those logs into Spark and do whatever analysis you want. Sensors, let's say there are some traffic sensors or temperature sensor or whatever, anything that continuously generates events. And if you want to do any kind of analysis on those events, then Spark is a great use case, like stock trading, bank transactions, like finding some sort of a fraud in real time from bank transactions. Things like that can be solved, are good use cases for actually using Spark. With these are usually like data that's very sensitive to how fast you process it. For example, a bank transaction for fraud analysis, you'll have to catch it probably within few hundred milliseconds, so that you can, just block the transaction from going through. Or stock trading, you usually have to respond within, again, in few hundred milliseconds, because money is on the line, and if you miss that window of opportunity, then the stock price could go up and you could lose money, etc. So it's very important to act and process the data as and when it arrives. So Spark, being like a real-time data processing framework, is great for these kind of analysis. And then, as I mentioned earlier, Spark stores all the intermediate results in memory, right? So it works great for iterative workload, which is a perfect setting for running any sort of machine learning algorithm. So that's why, like, if you want to run any machine learning algorithm on like huge set of data, then again Spark is used there. Usually Spark is used to train machine learning algorithms. And then Spark is also can be used for interactive analysis. Like you submit some query, it would crunch the data and it would give you the result. Like it would give the results pretty quickly. So you need not just use Spark for static analysis or static dashboard, but rather you can also, people like data scientists also use it for real-time interactive analysis. So it can be like any ad hoc queries that you submit to Spark, and then it would crunch the result and give it back to you in a reasonable time. So that way it can also be used for interactive analysis. And then data integration. So this is where we used Spark in my previous project. So we have like data from multiple different systems, like we were collecting data from few different microservices, we were pulling in data from Salesforce. So there were all of these different data sources which were constantly generating data, and the data is often unclean. So we used Spark to perform the ETL processing, where we collected data from multiple data sources. We applied some cleaning logic, some standardization logic. For example, if the naming convention is not right in the data, we would fix those. So any sort of cleaning, standardization, etc. was done in Spark. And then finally, once the data is clean and ready for actual analysis, you can just load them in any system, like let's say Elasticsearch or wherever you want the data, the clean data to be sitting, so that people downstream can actually like do some analysis on the data. You can make Spark store the data there. So that's how we used Spark. We just used it as an ETL tool to do some data cleaning and transformation, and we finally stored data in back in the Hadoop file system itself. And we were running different jobs on top of the cleansed data to do the actual analysis. We also used Spark for the analysis part as well. So we were using it for the ETL part, and also we were using it for the final analysis part. So I'll talk about all of this towards the end, where I would be talking about that whole pipeline. So these are the various different use cases. You can use it for real-time data processing, machine learning, interactive analysis, and also for running any sort of data integration and ETL jobs. So yeah, we have seen a lot of theory about Spark. Let's see some code. So Spark actually has three different kinds of abstractions. So the first and the simplest one is called RDDs. It's called Resilient Distributed Data Set. It's the most basic data abstraction, and it's very low level. Usually there are not many places where we directly use these RDDs. We most of the time use the other two abstractions that I'll be talking about next. But this is the most basic one. So a resilient distributed data set is nothing but an immutable collection of elements. So for example, here, let's say this is an RDD of a string and an integer collection, right? So there is John, 1, Tyrion, 2, and Ron, 3. Maybe it could be the name and the IDs. The way how RDD is stored is, here in this example, there are only like 3 entries, but ideally, like as I said, Spark operates on huge volume of data, right? So let's say there are like 1 million such key value pairs in this RDD. The way how it works is it's immutable. The RDD is the whole collection, but then the actual data can be distributed across multiple nodes. Like if this RDD has 1 million rows and there are like, let's say 10 nodes, then there could be like 100,000 rows of the RDD stored in each node. So any operation that you do on these RDDs would actually be done in parallel on these nodes. And that's why Spark is so fast. You can do any sort of transformation. For example, let's say you can do some sort of filtering, or you can group by something. Whatever you do on these RDDs would actually happen in parallel across all the nodes in the backend, and that's why it's super fast. And the way how you can create RDD is like, in this example, I'm just creating it in line from a sequence. But you can also like read, let's say you have that million entries stored somewhere in S3 or stored somewhere in Hadoop distributed file system. You can actually just read it directly from there and create RDD as well. So that is the resilient distributed data set. As I mentioned, it's a low-level abstraction, which we don't really use these days. There is something called as data frame and data set, which I'll be talking next, and that's the one that we use pretty commonly. So here in this code, as I mentioned, the driver program usually has Spark context. Spark context is nothing but, where is the Spark machine running? What's the master and slave node, the worker node details, and all of that. So that actually holds the Spark's context. And then we are creating like an RDD from a sequence that is hard coded here. I mentioned that we can do some sort of transformations and actions on RDD, right? So what are some of the examples? In this example, I am reading, I'm saying like, hey, use the content that is present in the text test.txt file to create an RDD. And then that's the first RDD. And then I'm applying a transformation on top of that RDD saying, hey, now from that file, take each word as one key. So that's why I'm doing like a split on the space. And now that would be the second RDD. So, and then in the third RDD, I'm saying like for each word that's there in the second RDD, change it to like an RDD of string and an integer. So like take the word and apply one to it. And give that as a third RDD. So here basically we're trying to do the same word count thing, but only for the words that starts with A. So at the end of RDD3, what we would have is the whole text file is split into words, and RDD3 will have the word and comma 1 for each word in RDD2. So now we are giving that RDD3 and we are saying, hey, take all of that, but only filter out the words that starts with A. So now let's say we had 100 words, and out of 100 words, we have like 10 words that starts with A. RDD4 will have those 10 words starting with A, comma 1. So now finally we are printing the count saying, okay, how many words are there starting with A? So that would get printed at the end. So if you see here, these are the different kinds of transformations, like a flat map, starting with, ending with. You can do like group bys, you can join by, you can count the distinct words, you can do intersections and all of that. So you can apply all these different kinds of transformations at each level. And then finally, action is something where you're producing some output instead of an intermediate result. Like you are saving the output in a file, or you are just taking the first entry and then giving it to the user, or here in this case, we are counting the number of entries in that RDD and returning that to the user. So the actual result that will be used by the user, it's actually called as actions. So that is the one that gives an answer. The transformations are the ones where you give it an RDD, you do something, and it would give another RDD as an end result, which is usually stored in memory. So you create an RDD, do a bunch of transformations like this, chain one after the other, and then apply some action on the final RDD and return the answer back to the user. So this is how you can write code using RDDs. The next abstraction is called the data frame abstraction. Here, this is a bit more structured. It's like you can think of it like a MySQL table. So it sort of imposes a structure onto the data. For example, here, if you see in the previous one, in the RDDs, we did not give any column names or anything of that sort. You can just create RDDs without any structure. But whereas if you see data frames, it's like an actual table. So you are saying this particular data frame has two columns, the name column and the ID column. So it gives that structure. And now you can do all transformations using those column names. So this is like more structured than RDDs, and that's why like this is the one that's more commonly used. So how we are creating data frames here, we are creating a data frame with name, DF with column names. So how we are doing it is we are again like passing an RDD to it, and then saying, hey, this RDD has two columns. The first column is called names and the second column is called IDs. And then if you just do the data frame name, the data frame dot show, it would just print that whole data frame. And then you can similarly do some transformations and actions on the data frames. Like here, I'm doing a filtering based on the ID field greater than 1, and I'm printing that. That's why like only Tyrion and Gandalf are showing up. So this is how we operate with data frames. Data frames is essentially like tables, and it imposes a structure basically on the data. You can also like you can create data frames by, again, here we are reading it from a RDD, but another way is you can also read it from text files. And it also supports different formats of text files. You can read it from JSON file, S3, you can just read blobs from S3 and create data frames. You can read Parquet files, which is also like another format of file like JSON, and then you can create data frames from that. You can, since this is like more structured data, you can do the data frame dot print schema, and it would actually print the schema of the data frame. Like here we had name, which is a string, and we had ID, which is an integer. So you can actually like look at the schema of data frame and all. And you can also run like SQL commands on the data frame. For example, here we have a data frame, and then we are running this SQL query, select star from this data frame where name is equal to John. And then that creates a result data frame. And if you print that data frame, you can actually see that particular entry in the data frame. So this is more, definitely, as you can see, it's more sophisticated than the resilient data set. So in my previous project, we extensively used data frames to process crunch data and to produce results and all of that. And the final abstraction Spark supports, it's called data set. This is like even more strict than data frames because here we are also imposing a data type. So it is strongly typed objects in data sets, which is not the case in data frames. So the advantage of data set over data frame is that type safety. So here in this example, let's see. Here on the top, I'm creating this data set called characters. But when I'm creating this data set, I'm clearly saying that this so if you comparing it with the previous one, here you're saying it's name and ID, you're saying, okay, there are two columns with this name, but then you're not associating any data type with it. So you can randomly still produce data with mixed data type and stuff. But what would happen is when you try to perform some operation on the data, that time if there are like inconsistent data types in the data, then there would be errors. So you will actually be hitting errors at the runtime saying, let's say you are adding all the IDs, right? And there is a string entry there. Then the program would fail saying, hey, I'm expecting all ints, but there is a string there, so I cannot add them. And then you'll have to go manually clean the data and rerun. So that's where data set is more advantageous, because while creating a data set itself, you are saying, hey, this would have two columns. The name column should only have string entries and the ID column should only have int entries. That way, even at the ingestion part, you can, catch the error, and you can catch all the syntax errors and the analytical errors even during compile time. Because if there is a mismatch right here, when you're creating these objects, you can't even compile the code, because it would say, hey, characters is supposed to take one string and int, but what you're passing a string to it. So it would fail right there. So you can avoid surprises at runtime. So that's why data set is even preferred. It's like it's more strongly typed than data frames. So here an example is we are creating, we are defining like class character, which would be the data set. So here we are defining the data set from this sequence of characters. There are 3 characters with their name and let's say their age. You can create it this way, or as I mentioned in the previous 2 examples, you can also like read it from some CSV file. And again, you can do operations, any filtering, any transformation and actions on these data sets using the column names, and you can do show that would print it. Basically the same thing on all 3 different Spark APIs. It's basically you are creating that object, be it an RDD or a data frame or a data set. You apply iterative transformations, and finally you apply some action and give the result back to the user. So this is the mental model that you should have. You create an object, do transformations, take some action, store it somewhere and give it to the user. Or the action can again produce some intermediate result which could further be transformed. So you could chain it however way you want it. So yeah, so these are the three different abstractions of Spark, the APIs that Spark supports. And data frame is the one that I have extensively used. So here, I just want to talk about the data pipeline that I used to work with in the past, where we used Apache Spark extensively. So the big data pipeline that I used to work on had both the real-time component as well as the batch component, and we used Spark for the batch component. So this was like a telemetry pipeline. So what we did was like we had, let's say, like thousands of instances of our services running somewhere, and they were like periodically emitting metrics to our big data pipeline. So all the metrics would be emitted via load balancer. There is a thin microservice at the beginning of the pipeline, which job is to just receive data from load balancer and store it in Kafka, because we can't do heavy processing here. Otherwise, all the metrics here would get backed up. So this is a very lightweight layer. All it does is it receives it and writes it into Kafka. So the real pipeline starts from Kafka. We bifurcate into two different pipelines. In the real-time pipeline, there used to be a set of microservices that reads data from Kafka, does some transformations, cleaning and all of that, and writes the data into Elasticsearch. And we had like another microservice on top of Elasticsearch, which was essentially used for real-time querying of data. Like customers would just query APIs and get the results. We also had UI that was powered by this microservice. So essentially, this is the real-time pipeline. If you talk about UI, dashboards, charting, all of those are usually like real-time data, right? So those use cases were handled by this real-time pipeline. But we also had this batch ingestion pipeline, where again, we had a set of Spark applications that were reading data from this Kafka cluster. It did all the, some initial cleaning and transformations, and it stored the output of those results in a Hadoop distributed file system. So these jobs used to run all the time, like every 15 minutes or so, they would produce some intermediate result and store it in the Hadoop file system. And then we had another set of Spark jobs that were running like once a day at midnight. So what those jobs would do is they would again coalesce all the intermediate results that were generated by the first set of jobs throughout the day. It does some more transformations on the data that's like for the whole day. And then the end results of crunching the whole day's worth of data is again stored back in Hadoop distributed file system itself. So this is where the Spark jobs were being used for the ETL process. We were cleaning, transforming, crunching, and then the final result is stored in Hadoop. And then that's where, and that final clean data was then used by different people in the company, like data scientists, product managers, etc. And they are the ones who wanted to do analysis on this data. So there, what they do is each one of them, they would write their own jobs. They're like, hey, I want the past 1 week's virtual machine related metrics. I want to know how many machines were spun up. Did we onboard any new user? It could be any use case, right? So they know the structure of the data. They would write jobs that works on the data, and they would submit those jobs to a different Spark cluster, which again read this processed data, crunches whatever information they want, and it would return it back to those internal customers. So that's where we used, like, this is how we use Spark for two different use cases, for the ETL process and also for the actual data analysis itself. So yeah, so Spark can be used in both the approaches. We also use Spark for interactive analysis, like I said. So we had something called as a Zeppelin notebook. You can think of it like a notebook, like an environment where you can go write any code, press the run button, and it would just spit the result right there in few minutes. And then you can iteratively just change the code, press the run button, and it would again like give the results in few minutes. So it's like an interactive analysis, and we were using something called as Zeppelin notebook to perform that on top of Spark. So we were essentially using Spark for all of these different use cases. We just did not have any machine learning algorithms running. That's the only thing that we missed. Now, pretty much like that is an example Spark pipeline that I have actually worked on in the past. Now I thought, okay, I'll just run like a basic Python Spark code on my MacBook and then show like a demo.
Harini, maybe just before the demo, you could take this one question. I think me asked, can you explain what kind of data do you process in batch ingestion pipeline?
Yeah, so I can give like a few examples. The one that we processed in this pipeline is essentially the metrics, the operational metrics from like a bunch of different services that were running. Like, let's say we had like 1,000 machines running, and those 1,000 machines were emitting metrics about themselves. For example, like, the disk space, the CPU utilization, like thousands of metrics about those services, and they were all being published into Kafka. So this batch processing pipeline was essentially crunching metrics that were published by these data sources. Another example could be, like I mentioned, you could be collecting some temperature related data from sensors that's installed across the city, and your Spark pipeline could be used to crunch the temperature data, and you could derive some insights from that. It could be any real-time data. It could be some stock market trading related data is a good example. Bank transactions is a good example. Anywhere, or log files, anywhere you think of data being like continuously generated at high volume, and you want to do some analysis on the data, then you can use it, and then you can use Spark to do that analysis. Does that make sense? Yeah.
Yeah, please post again if anyone is not satisfied with any of the answers that I put in the chat as well, and we'll bubble it up to Harini after the demo.
And I actually have saved this presentation already in our Women Who Code GitHub repository. So if you're interested in, running Spark locally on your laptop, you can just, this slide also has the link to this demo. So you can just follow the setup. You need Java environment because like Spark is written in Java and Scala. So you need that. So you install Java first, and then you install Spark. You set up some environment variables, and then finally you can try running the simple code. and you can just submit the Spark job and it would run the Spark job and it would print the word count for you. So I'll run and show it in a bit, but just going over the code. The first one is the Spark session where you're saying, I'm going to be running an app, a Spark app, and the name of the Spark app is word count example. And this word count example Spark job is going to read data and create an RDD from this example.txt file. So that's the input data. And then from that RDD, we are again doing the same thing. We are splitting it by space so that we can get each word. And we are saying for each word, convert it into a sort of like a tuple with the word comma 1. And then finally, we are reducing by the key saying for each tuple, just add all the ones and finally give me like all the word counts in this format, like word and its count. And then once all of this is done, the Spark job can be stopped. So the entry point would be in the driver program, but all of this actual crunching on the RDDs would actually be happening on the slave nodes. So that's how internally it works. And this Spark cluster manager is the one that orchestrates all of this. So just to run and show it locally, this is the same word count program that I showed there. And I named it words.txt. So this words.txt essentially has like a 44 lines of text separated by space. So now if I just run the Spark submit job, I installed all of this and have everything set up already. So now I'll be just doing the Spark submit. And now you can see that it would print ideally it should work. Yeah, Spark is started. It usually is pretty heavy on the text that it spews. So you see executors are getting created. The mappers are running, like the tasks are running. The input RDD is created from the input file, like it is created, split into 2 splits and everything. Since the data is so less and it's a pretty simple code, all the processing happened within like few hundred milliseconds. And then you can see that at the end, we wanted the word and the count to be printed in this particular format. So it actually like just did that. It printed the whole output on the screen. If we had done save as a file, it would have saved this whole thing as a file. So I just printed it in the code. So it is just printing it on the screen. So yeah, if you are interested in trying it out, you can just follow the tutorial and run the same thing, and you can try tweaking the code and see how the output changes and things of that sort. So this is like a good example code to or a demo code to just get started off with if you are interested in learning more about Spark. Yeah, pretty much with respect to Spark, that's all I had for today. I have put all the references that I used to create the slide deck on the last slide. So you can go over these references and read more if you are interested. We also have some interesting sessions in the backend study group coming up. There's one more this month, and we at least have one session every month. Sometimes we even have like 2 or 3 sessions, but these are the scheduled ones. So please check our meetup page and RSVP to the sessions if you haven't. All the recordings from recent sessions are also there in our YouTube channel. So if you are interested in watching the older recordings, you can go and check them out. We have all the presentations available on GitHub, so you can check those out as well. Yeah, if you have any questions, you can raise your hand and I'll try. I can unmute you, or you can post it on the chat. and I can respond there as well. And I hope Ashwini already shared the links to all the Slack channel, the GitHub space, the YouTube recording and everything. We have also posted our LinkedIn URL there. So if you have any questions, feel free to reach out to us either on Slack or on LinkedIn. Yeah, is there any questions? Open questions?
Yeah, I'll post the information again.
Okay.
Just posted it again.
Perfect.
Yeah, I think I have answered all of them, but if I've missed any or if you still have questions, please do post and we'll get Harini to address them.
Yeah, you can also, if you have any questions later at any point, feel free to post it in our Slack space, and I can answer them there as well. All right. Thanks for joining the session today, everyone.
Thank you, everyone.